So let's consider a function given by this Maclaurin series. All right? We could ask, what is the radius of convergence of this series? Now we have to be very, very, very careful in order to identify what these coefficients are. Remember, if I did all right, this series, the radius satisfies that equation. Here, we have to be very, very, very careful, because what governs the fact that this is CK is that it is coupled with Z to the K. Here, I have one over 2 to the K coupled with Z to the 2K. So my radius will look like this. The 2 to the K root of 1 over 2 to the K. All right? So let's see what that gives. All right, I'm going to have 2 to the minus K divided by 2 to the K. Now, if you plug in a couple of numbers, it should be obvious that as K tends to infinity, K divided by 2 to the K tends to 0. So this limit is 1. That means that this series converges on the unit disk. All right? Now, let's think about what the behavior of this series is on the unit disk. Or sorry, on the unit circle. On the unit circle, the modulus of Z is 1. So I could sum this up. The modulus of the numerator is just 1. So this converges everywhere on the circle of convergence. All right, but let's see what this function's behavior looks like on this circle of convergence. I'm frozen. Oh, there we go. All right. So I'm going to go ahead and define this function, all right? It would be the sum of Z to the 2 to the K divided by 2 to the K. K runs from 0 to N. All right, and I'm going to do parametric plot, the real part of f of Z, and let's make it 10. And then its imaginary part. And we're going to make Z e to the IT. Okay? All right, so let's see. Ooh, it needs to be FCN. Oh, it didn't work. All right, real part of f of, oh, it's because I did this. Oh my gosh. And there we go. We get this very interesting fractal form. And if we want to know why, we can see it immediately. If I take a derivative of this, the 2 to the k is going to cancel out. And this derivative won't converge anywhere on the circle of convergence. We'll talk next week.